One World Combinatorics on Words seminar. Our speaker today is Annika Huch from Kiel University, and she's going to talk to us about a word reconstruction problem for polynomial regular languages.
Thank you so much for the introduction, and thank you for inviting me to have a talk in the seminar. Yeah, as Narat just said, I will talk about polynomial, the reconstruction problem in polynomial regular language, which is a joint work with Mehdi and Michel, who are both also here. So yeah, in case you have more questions. And we did this work together when I was visiting the university. So yeah, let's go directly in and start. Yeah, I will first introduce the reconstruction problem. Probably it's not that much new to all of you, but I thought maybe some of you don't know reconstruction problems in general. Then I will talk about polynomial regular languages, our translation to polynomials for this reconstruction problem, and yeah, two cases of this reconstruction problem. First, we investigated the nice case of two loops, and then the general case where we had some problems, but even there we were able to get some results. So let's start. First of all, we are looking on scattered subwords. What does it mean? We have some transmitted signal like banana, just a toy example, but something gets lost in the middle and we only receive a subword of it. So some people call it scattered factors, some people call it subsequences. Yeah, all the same term. But the main important thing is that we should not violate the order. So yeah, BA would not be a subword of banana because the order is violated. Okay, I hope this concept is clear to most of you. And the reconstruction problem asks for uniquely determining an unknown word from a set of queries, which means, okay, we have some reconstruction queries, and in our setting, they are subword queries. So we ask, okay, how often is the subword Q contained in the subword G? And then uniquely determine this unknown word G from such queries, which we send and then retrieve integer values. I have a short image for this. We have some unknown word. We query some words that are hopefully subwords of the unknown word and get back those integer values, which say us, okay, yeah, Q1 is some integer value often contained in G and so on. And with this, we want to reconstruct G. In literature, there are different variants of this problem. One variant is to query all words of a certain length over the alphabet sigma and find the smallest such value, such that we can uniquely reconstruct L. And there are some bounds. So many people investigate this. I just looked up to my knowledge, the most recent best bound on this, and it grows in the word length. So yeah, this is just one variant. And another variant is to adapt the query on the result of the previous query. So if we query something and get to know that there's, for example, no A within this word, then we do not need to query any other thing that has A in it. And there are also some recent results, for example, by Huch and Rosenfeld. And our variant of this problem, which we investigated now, is the reconstruction of a word from a specific regular language. So we decrease the search space, so to say, and we want to only investigate regular languages with polynomial growth. What does this mean? Well, a regular language has polynomial growth if the number of words of length n for every length n is bounded by a polynomial. So yeah, maybe the most interesting, or for our work, the most interesting result on this was found from Zilat et al. In 92, but there's plenty of research on polynomial regular languages. But this result states that every polynomial regular language is a finite union of languages of a really specific form, which is this. So we can have like some word, and then we can have something like a loop with the star, then we have again a word, and so on, which essentially means that if we have an automaton like this one, so those can also be more states. It's just a simplified drawing, and here we can also have more states. But if we have a word here and like path with a word here, then we are not allowed to be able to take two different loops from the same state. Okay, that's the general structure, and this is what we will make much use of in our complete work. So we translated we specified the reconstruction problem. We still have an unknown word. We query, again, some set of T queries, but now we know that the word is contained of some polynomial irregular language, but we don't know the values of the exponents. So we know the words for sure of this form, and we get back the integer values, and our goal is now still to reconstruct the guess word, like, the unknown word, but we need to, the only task, only in quotation marks probably, is to uniquely reconstruct those exponents of the loops. Okay, so how often did we took the loop in the automata? So for example, one word would be going here, taking this loop twice, and then just following the path, just as an example. Okay, and in order to do so, we translated first of all the queries, because we know the guess word is of a really, really specific form, to polynomials. What does this mean? Let's do an example first. If we have, for example, this automaton, which is a polynomial regular language. So we have just one loop, and the condition is fulfilled. And if we query the word 0, 1 here, then we get, okay, how often is 0, 1 contained in, oh, sorry, I cannot just mark the upper part, but in 0, 1, 0, but since this is a loop, we can enter the loop x times, which is just some variable, and then we can split it up with, okay, we can either find the query, I will mark it here, 0, 1 with one pass through the loop, so within this word, or we can find a 0 in the first iteration in the loop, and then a 1 in the second iteration. And that's how we started to look at those polynomial regular languages. And the thing is, okay, we have here this exponent x, which tells us how often did we took the loop. If we take 1, 0 in one iteration of the loop, we get the binomial coefficient x over 1, which is just x. And if we take it from different iteration of the loops, we get the binomial coefficient x over 2. Which you can simplify, but the main thing I wanted to tell you is just that we get here a polynomial, which or an equation which is a polynomial in x. Okay, so this leads to the first lemma. It's just a generalization of the thing I just showed you in the example. If we have some v to the x over u, we get this thing here, which means, okay, we have all possible factorizations of u into 1 to u parts. So we start with u not factorized until we factorize it into letters, and then we just take the binomial coefficients of the loop separately with the factors, and then times x over the number of factors. So this here is just the part of the equation from below for I equals 2. Yeah, exactly. That's why we have x over 2 there. Okay, in case there are any questions in between, feel free to type in the chat or something, or ask later. So I hope this gets clear. And we generalize this one for the large setting. So the first step is to have for all words and all queries we are proposing, we have this form, or like this, this equation, which I go back one step, which is the inner part of this equation here, sorry, without x over I, which we take as coefficients for our polynomials, okay? So those here are the coefficients for the polynomials. They're independent of the power x. And then as a second step, we want to glue them together. So we take the part which is dependent on x, define it as B. So if we have a word we and do not query anything in the loop, then we obtain 1. So not query if we query the empty word. And if we query some u, we have here all possible factorizations of u and times the binomial coefficient over I, as I just showed before. This is just some notation. And the thing here is, okay, if we query, so if u is contained in the loop and we query some word u, then this coefficient is not, this alpha coefficient here is not non-zero, which means that the degree of this polynomial is the length of u. Okay, this is quite nice, because then we know with what kind of degree of polynomials we have to deal. But this is rather formal. Let's make an example. So we again have this language, and let's see what happens if we evaluate first an abstract and then we make a more concrete example later, g over q. Okay, what does it mean? We take all possible factorizations of our query q, and well, then we can find the first factor in the first part of the polynomial language u1. Then we search for the second part f in v1 to the power of x1. So we can take the loop x1 times to search f1 here, then search e2 in u2, and so on. Okay, so this is the first thing. And I think you might notice, but this is, we can split it up like this because of the Schur-Vandermonde identity on binomial coefficients. So this is just the same, and we can rewrite this one. So this equation here, which I just showed you, into this part. So first collecting all the u's, because they are fixed. They do not belong to any parts with variables. So collecting all the u parts, and then adding those b polynomials, which I showed you before, that exactly represent the parts where we have v to the power of x over something. Okay, so this is our polynomial, which is really nice. It is a polynomial that represents the guess g over q, and if you remember from the setting I told you, g over q returns an integer. So we have here some polynomial, which we call pq from x1 to xt, which is equal to this value, which is, for our knowledge, in the setting of reconstruction, just an integer, and we don't know what g is. So this polynomial has, as we said before, degree at most q, because every of those here, b polynomials, has at most degree q, and t variables x1 to xt. And furthermore, it is completely independent of the guess, which means, as I said before, this one here is an integer value, and we have here some polynomial equation with t variables. Okay, so let's define this equation, which I showed you just a second ago. So for this polynomial regular language, we consider this as the this as the equation, polynomial equation, and with this really reduces our problem, because if we have a guess word from a polynomial regular language, then the tuple of those exponents is a solution for this equation if we have that this equation is equal to 0. Okay, so if we solve a system of polynomial equations with those equations, then we can reduce this problem to finding a set of queries such that the system of equations, which is as large as many queries we pose, and if this system has a unique integer solution, we have found the guess word again, because the integer solution would then just be the exponents of the guess. Okay. And now we're finally coming to a more concrete example, not just to the calculation I showed you before. So this is the polynomial regular language of my choice for this example. So this is u1, v1, and so on. And what happens if we ask the oracle, what is g over 0? we return some value 21, which is just, we don't know why, but we can calculate what g over 0 is 2. So g over 0 is how many zeros do we find in u1 plus how many zeros do we find in v1 times x, because we can execute this loop multiple times, plus how many zeros can we find in u2, plus how many zeros can we find in v2 times y. I just used, and we did in the joint work in the paper too, we just used here x and y instead of x1 and x2 for convenience and overview. Okay, so we can calculate this. u1 over 0 is just 1. Here's 1 0. And we have 3 zeros times x, 2 zeros, and again 2 zeros times y. So we get 3x plus 2y plus 3, which is a linear equation. We can just plot or look at. So we get this equation first of all, which is just this one here. Oh, sorry, I made a typo. It should be minus 18. Sorry for that. Here should be a minus 18 because we need to subtract the. Oh no, it's correct. I just haven't evaluated it. Sorry. So we have minus 3 minus 21 because we know that this equation here minus over our guess must be 0. Okay, so we can also do it for an even bigger word. This gets a little more sophisticated. That's why I have those brackets there to get to keep the overview. So if we query 1 0, we get this large value here back. Okay, so let's start with those parts which belong to the same factor. So we ask, okay, how often is 0 1 contained in u1, which will be 0 times, but I will just write it down for seeing how this procedure works. Then we have how often is 0 1 contained in v1 times x. How often is it contained in v1? But first, just asking for the 1 in the first iteration and then asking for the 0 in the second iteration. So we get this binomial coefficient as with the loop before. I hope you vaguely remember it. Then u2 over 1 0 and v2 over 1 0 times y, and then again this the splitted up part. So we obtain this one. Okay, and then we can also, for 2 letters, we can just choose the 1 and the 0 from different parts, which means, okay, from different factors, we can choose the 1 from u1, which will be 0 because there is no 1, but I just wanted to write it down for seeing how this procedure works. And then the 0 from any other part. Then we can find the 1 from v1 times x, because there's this loop, times u2 over 0. Then we have v1 and v2 as combination. Then we get here this this multiplication of both variables. So you see it gets more and more sophisticated the more loops and the longer the query is. And last but not least, we have the combination of u2 and v2, so times y, because we have the v2 loop here. Okay, and this is all calculable, I guess. So we have no 1 0 in u1. We have 4 times 1 0 in v1. So 1, 2, 3, and 4 here. Okay, then this we can also calculate. We have 2 1s in v1, 3 zeros in v1, and x over 2 is just evaluates to this one here. So this fraction. Yeah, and then I will just go a little faster through. We have 1 0 one time here. Then we have 1 0 again one time here, so plus y, and 1 1 and 2 zeros in v2. And again, we evaluate the binomial coefficient. So the first bracket here are just all factors from the first bracket above. And then we add the ones from below. So no 1 in u1, so 0, plus 2 1s in v1 and 2 zeros in u2 times x. And where are we? 2 1s in v1 and 2 zeros in V2 times xy, which is the mixed coefficient of both loops, and 1, 1 in U2, and 2 zeros in V2. So this is the thing we get, and now I'm simplifying this. I just heard that the slides are going to be uploaded, so you can check the calculation later if you want to, but we obtained this one, and Michelle also checked with Mathematica. But this is really nice because we can, we have this equation and we can look at it as a plot or something like this. So let's see, we queried, what have we done? In this example, we queried 0, obtained this equation for the polynomial and this as the guess. We queried 1, 0, obtained this large polynomial, which we just calculated, and this was the guess. And when querying this one, I will not do this with you together, you get this large polynomial, which, as maybe to remember, the query is of length 3, so we get degree 3. And also we get here those mixed polynomials can be cubic because, well, the 0 can be chosen from V1, and both 1 and 1 can be chosen from V2. Okay, then we get this, y cubed here. Okay, and this system, now we are searching for the answer if the system can have a solution or has a unique solution. If we query for those two here, we get that there are two solutions. First of all, this one here, which is an integer solution. So with our knowledge, with the semantics, that solutions to our system must be integer solution, because we are not considering fractional powers in polynomial regular language. There's nothing like taking half of the loop and then skipping out. And also we do not consider negative answers because there's no definition of going a loop negative times. We add the large polynomial, which I just showed you, and then we obtain a unique solution. And how does this look like? It looks like this if you plot it. And this is the intersection of all of those polynomial equations, which has a unique point here. So our solution, we can just read it from this thing here, is 4, 3, or we can also just look here. So we get back this guess word by just plugging in again x and y. Okay. So then we started to look at the case of just two loops, which first of all might seem too easy or a little easy for you, but I will show you why this is even slightly hard to evaluate. Okay, so the language is of a really specific form. So it's just this one. We don't have t loops, we just have two. So our examples and before for this presentation were also small, but we know for sure that we have this exact form. Then our guess word is exactly of this form too, with x and y. The equation can be just evaluated up to this form because we know we only have two loops, so we have only two b polynomials and 3 u parts, which is u1, u2, u3. And for letters, we have the specific form that if we ask a letter A to the query, we know, okay, how it evaluates to how often is this letter contained in V1 times x, how often is this letter contained in V2 times x, plus how often is the A contained in the U1, U2, U3 parts. With this notation, with the bar and the A in the index, I just mean the number of occurrences of this exact letter. Okay. So the first result we got there was we have a language and we have those coefficients given. Then if the two Perec vectors of V1 and V2 are linear independent over Q, then we get that we can uniquely reconstruct any word or any guess word in the language with two queries. And both of the queries are of length 1. So let's have a look into this. Why does it hold? So we queried this one here, which I just showed you is this equation. And we query a second letter, which is just the same equation with b's in the index. But now we know the Perec vectors are independent. So we know that VA, so the how's it called? The acceleration, I think, like the steepness of the linear equations is the same. So not the same because they're independent, not the same. So those are two linear equations with one exact point of intersection. So what does this mean in our case? If we have the example just from before, so the one we evaluated in before the whole time, we saw before that this is the guess word and this is the solution because we already did this example. But if we query just those two, we haven't done it before. We only calculated g over 0 before. So I just give you this one. Then we get this image, which is, okay, two straight lines with one unique point of intersection. So we know that there's the solution, and we're just fine. But the problematic case is now if those two are linearly dependent, because what does it mean? It means that our two equations are equivalent. So they are representing the same line. Let me go back on this coordinate system if we are plotting them, because they cannot be parallel, because we know that the guess word is from this polynomial regular language. So there needs to be at least one solution, and we just need to reduce the solution space for which we know that isn't empty to just one integer solution. So those cannot be parallel lines because then they would not have any solution. So we know that those two equations are equivalent, representing the exact same line. So we try to query just one letter and a two-letter word. And we got the result that, again, for such a language, and we have that those two are co-prime and binomial equivalent with value 1. I will go into detail what this means later. And there exist two letters such that this huge thing here is non-zero. Then we can also uniquely reconstruct the guess word within the language with two queries. As I teased here before, one query with one letter and one query of length 2. Okay, so what is this huge thing here? Maybe to give the intuition, this just tells us, okay, the things we are querying are, again, one linear equation. And this thing here, as you remember, the polynomial is always as large as the size of the query. So of 2, so we have here a parabola and a linear equation. And by asking for this big thing here, which I will explain in a little moment, we make sure that the parabola and the linear equation have the same orientation, so we can make sure that there's a point of intersection, not that they are lying here, such that they do not intersect. Okay. Let's see how this looks. So this here is the big frame just copied from before, and let's see what happens if this one is 0. So if the condition of this form is violated. So either we have that those two are equal and those two are equal. Okay. And then we obtain that those two words are two binomial equivalent because it holds for all letters. So this one here is just a definition of two binomial equivalents, and that our Pyric vectors of v1 to the alpha and u2 are linearly dependent, or that those two are non-zero. So as I said you before, if this is the case, we have the problem that there might not be any point of intersection or a non-unique solution to the system. But now let's first make an example. So if we have, this is now a new example because the other one was solvable with two queries of length 1. So new example. And we now have here that the Pyric vectors of those two loops are dependent. So we have here 2 zeros, 3 zeros, and 1 0 and 2 zeros. So they're dependent of a Q. And we have those three equations. The first two equations are just not visible in this, or one of the first two equations is not visible in this picture because they are, again, the exact same line. But the third equation over 1 0 is this parabola. And with the condition, with the big condition I showed you before, we make sure that they both have the same like orientation or axis. and thus we know for sure that they have a unique point of intersection. Okay, as a consequence, we know that we can always run into this problem with the binomial coefficient. So if we again have the setting of polynomial regular languages, and we know that they are one equivalent, so just as in the slides before, where we discussed this big equation, and we have some k which is greater than 2, such that we have a long enough guess word, then q, and for all queries, we know that those, all queries between 2 and k, we know that this set of polynomial equations gets the same set of solution if and only if we have this k binomial equivalence. So at this point, there was, nothing we were, how to say it? At this point, we're not able to do anything with queries up to length k, because we knew then, okay, they would be equivalent, which then results, as in the slides before, to the same sets of solution on those equations. Okay, so what did we learn from that? We know that we can choose some largest k such that we get that this binomial equivalence is violated. So the trick, so to say, we used is to determine if we have this binomial equivalence, determine a large value such that those are not equivalent anymore, and then so the largest value such that they are equivalent, and then query 2 queries, one of length 1, and then a second one of length k plus 1 to make sure that we again have a point of intersection by the argument on the orientation of the geometrical objects we get from there. Okay, so the complete picture for 2 loops is now. We ask, okay, are those 2 loops linear dependent? If they are, linear independent. If they are, then we can ask for 2 queries of length 1 and get a unique integer solution. This can also be generalized. If the alphabet is larger, then we can just ask for as many queries as the alphabet sizes and still get this result, also for equally many loops as alphabet size. If they are linearly dependent, then we ask, okay, are there one binomial coefficient, those 2 powers of the loops? This means that they have binomial coefficient, and we ask if this big equation I showed you is 0 or non-zero to determine the orientation of the graphs there. If it is non-zero, then we can ask for 1 query of length 1 and 1 query of length 2. And if it's 0, then we have to find the largest value k, such that the binomial equivalence gets destroyed. And we ask for 2 queries, one of length 1 and one of length k plus 1. So it's quite nice for the 2-loop case. In any case, we were able to find 2 queries that solve the problem uniquely for us. So then we went to the more general case, which is a little more complicated, because you see, this already got really complicated here in the 3rd step. So we started with more loops. So we might probably ask more queries. We have a larger system of m equations. But the thing is, we know, as I said before, that there exists at least one non-negative integer solution. Okay, so we know we know that there is a solution which translates the problem to showing that this map here is injective. So what is it? It's a map from our variables to the polynomial equation we had before. And what are we doing with this map? So we're taking it. It's first of all the map over the natural numbers, but we decided, or we read it as a map, or extended this map to the domain of real numbers. So it looks like this, just extended the domain, which means that we can apply so first of all, we can express it in first order quantifier logic. And then we can use the Tarski-Seidenberg theorem, which says that for every first order formula over the real field, there exists an equivalent quantifier formula. And there's an explicit algorithm to compute this quantifier formula. So we have this formula, and we can conclude from this that if we have this set of queries and the corresponding polynomial map, and if the quantifier elimination returns true, so if we are able to get rid of the quantifiers, then we know that any word in this language can be reconstructed with this constant number of queries. And if we have chosen not enough queries, then the quantifier elimination would not work. Okay. So this is the main result we were able to get for the arbitrary case, or not arbitrary, but for a larger polynomial regular language. And this here is just the overview picture. So what have we done? We took the word reconstruction problem, edited it to the binomial coefficient, not binomial coefficient, to the polynomial regular language case. Thus, we knew that the unknown word is of a really, really specific form, and that we have a unique integer solution to our system of polynomial equations. Here are three pictures on the case, two pictures on the case of two loops. So either we have two intersecting linear equations, one intersecting linear equation with a parabola, or we can query a higher binomial coefficient, a higher binomial equivalence value, such that we still know that we only need two queries. And in a general case, we translate the polynomials to this map, which needs to be injective in order to guarantee a unique solution. And this can be decided via the Tarski-Seidenberg theorem, as I showed you before. This was it from me, and I'm happy to try to answer any questions from your side.
Thank you, Annika. Does anyone have any questions? Hajime.
Thank you for a nice talk. My question is the case of three loops. Of course, it's generally difficult, but is there nice situations that so there exists a useful complexity estimate for uniqueness problem of query?
Like especially for three loops, or
yeah.
I didn't know. I think we haven't looked at the case of three loops because this year is like the theory of conic sections, and this exists for two variables. So with this matrix, and you get the orientation of this, but I think it gets harder in the three-dimensional case because you cannot have this nice geometric representation because you are not sure to have a point of intersection if you have the same orientation. But maybe I just don't know enough about such kinds of graphs in three or more dimensions.
Thank you.
Okay.
Does anyone else have a question? So I had one question. So with this Tarski-Seidenberg decidability, did you implement the algorithm to do this?
No, but Michel introduced me to Mathematica. I haven't known before this project, and there's a Tarski-Seidenberg implemented already. So we used it and showed that it's the quantifier elimination works for our examples.
Okay, cool. Okay, so it's
so there are implementations out there. Yeah, exactly.
Okay, cool. Are there any other questions?
I don't know if you're interested in the code. Michel linked the Mathematica code to the it's not published yet, but it's on this Liège pre-submission server.
Oh
I
yeah,
don't know
okay.
how it's called. And there's the paper, and there you can also have a look at the Mathematica code if you want to. So yeah,
Oh, interesting. Okay.
maybe just Google, I think, a word reconstruction problem for polynomial regular languages, and then you should find it. Or if you don't find it, you can send me an email and I'll share you the link.
Okay. Great. Are there any other questions? Okay, thanks again, Annika.